Hello and welcome to our lesson on the other trig functions. So we spent a good amount of time focusing on the sine curve and the cosine curve, and those two are really the foundation for the other trig functions anyway. But they are the more important of the trig functions. They're the more commonly used, they fit more situations moving forward, and they're used more often, more frequently. So it's really important to know all of the details for those two functions. Now, the others, the tangent, cotangent, secant, and cosecant, aren't as commonly used or referenced, but it will be nice to know what the graphs look like, why they look the way they look, and be able to recognize them when you see them. So we're going to spend a little bit of time today graphing the old-fashioned way by making a table, by reading the unit circle, so that we have a concept of how the other trig functions look graphically, and again, so that we can recognize them. But ultimately, we really want and need to know about sine and cosine, and this is going to be some nice to know information. Okay, so we're going to start with the tangent. Again, graphing the old-fashioned way. We're going to make a table, and we pick some values for theta. We figure out what the tangent of theta is. Now, before we get started, we remember what tangent is, I'm hoping. So when we're looking at tangent, on our inner right triangle, we know it's a ratio of the opposite side over the adjacent side. But we said in the unit circle, we're going to find the tangent by taking the y value and dividing it by the x value. Well, the y value is our sine. The x value is our cosine. So really, we should be thinking about the tangent as the sine of x divided by the cosine of x. Okay, so it's sine over cosine. So let's look. It's sine over cosine. Now again, we're going to be using the unit circle, so if we just want to think y over x, that's fine. And really, we're going to use thetas. So let's say sine of theta over cosine of theta. And that's a little squished. So let me move this somewhere, like maybe here. Okay, whatever, that's good. So let's look here. If we're looking at an angle of 0 degrees or 0 radians, and I wanted to know the tangent, I would take the sine and divide it by the cosine, the y value over the x value, which is going to be 0 over 1 or 0. And just for convenience, I'm going to skip through all this ugly stuff, and I'm going to go to pi over 2 radians. Pi over 2 radians, if I take the sine and divide it by the cosine, the y value over the x value, I get 1 over 0, and that's undefined. Again, for convenience, I'm going to fast forward to pi, and at pi, we're dividing y by x, sine divided by cosine, we get 0 again. Fast forwarding to 3 pi over 2. At 3 pi over 2 radians, we have sine over cosine, negative 1 over 0 being undefined once again. And then fast forwarding back around, full circle, back to 2 pi. We're back to where we started, where we're at 0 again. So right now we know that this graph is going to cross at the origin, 0, 0, we have a point. At pi, we're at 0. And at 2 pi, we're at 0. Now, in the middle of those, at pi over 2, we're undefined, and at 3 pi over 2, we're undefined. And the reason we're undefined is because we get a 0 in the bottom of the fraction. And 0 in the bottom of the fraction, being undefined, does the same thing graphically that it did with the irrational functions. It creates a vertical asymptote. So we're going to have a vertical asymptote at pi over 2, and we're going to have a vertical asymptote at 3 pi over 2. Now that's all we put in the table. That's not really enough for us to make a complete picture. So we're probably going to want to figure out at a few more angles what's happening with our tangent. So let's go ahead and go through a few more. Okay, let's say we wanted to look at pi over 6 right here. Pi over 6, if I take my sine, 1/2, and divide it by my cosine at radical 3 over 2, what happens? Well, I don't divide fractions. I would multiply by the reciprocal. So if I multiply by 2 over radical 3, those are going to cancel, and I get 1 over radical 3. Approximately, let's see, 1 divided by, let me just clear all this out. 1 divided by radical 3, it's about 0.6. So at pi over 6, we're at about 0.6. It's going to be like here-ish, okay? And then at pi over 4, pi over 4 is not bad. I'm going to be dividing something by itself, which means I'm going to get 1. So pi over 4 is right in the middle of pi over 6 and pi over 3, so I'm going to be at 1 there. And then when I go to pi over 3, I'm going to have radical 3 over 2 over 1 over 2. Again, that's going to be multiplying by 2 over 1. So I'm just left with radical 3, and radical 3, I believe, is about 1.7. Yeah. So radical 3, or at pi over 3, I'm at about 1.7-ish, so somewhere around here. So as we continue, you can see this graph is going to increase. What we have to be doing is approaching that asymptote. So we are increasing as we approach this asymptote. Okay? So now we're going to jump over the asymptote, and we're going to see what's happening on the other side. Well, we're going to end up with the same values. We're just going to be changing signs because we're changing quadrants. So when I'm looking at 2 pi over 3, 2 pi over 3 is right here. That's radical 3 over 2 over negative 1/2 again. So that's going to end up being radical 3, which was 1.7, but this time it's negative. So at 2 pi over 3, I'm at negative 1.7. So that's like down here. And then at 3 pi over 4, I'm going to get negative 1. So right in the middle here, I'm at negative 1. And then at 5 pi over 6, I'm going to end up with the reciprocal of this, which is going to be 0.6 again. So 0.6-ish again, like this. And so it looks like we are approaching the asymptote this way. So we're still increasing, okay, but we're coming the other direction from the asymptote. And then what happens when I go to the next quadrant? So we're going to get the same values again, and it should make sense that our values are repeating in this periodic function. So let's go to 7 pi over 6, that's here. So that's a negative 1/2, and a negative radical 3 over 2. Negative negative makes it a positive this time, positive 0.6. So positive 0.6-ish, somewhere around here. And then here we're going to get a positive 1. And then here we're going to get a positive 1.7-ish again. And so we can see that this graph is going to be heading toward the asymptote again. And then what's going to happen is the same thing when we jump over the asymptote. So we get into this quadrant and we're looking at the same values, but they're negative again. And so we're going to see this happening. We're going to be, and I didn't draw that very nicely. It's going to be this type of deal happening. Okay, so there it is. There's what basically your tangent graph is going to look like, and that's just going to continue to repeat as you move along. And I erased a little too much, but let me just confirm with you. Okay, let's go ahead and put it in Desmos so we can see it. If we graphed y equals the tangent, what am I doing? Functions, tangent of x, and there it is, same picture that we just put on the graph. Okay, so there's the tangent of theta, where the tangent of theta ends up having these vertical asymptotes where cosine is equal to 0. And why is it where cosine is equal to 0? Well, because that's where that's what we have in the bottom of the fraction. So anytime there's a 0 in the bottom, we end up undefined. So we have vertical asymptotes where our cosine of theta is equal to 0. So cosine was equal to 0 at pi over 2 and at 3 pi over 2. Okay, and then there are branches that are in between the asymptotes there, and those branches are constantly increasing. Increasing. So we have branches in between the asymptotes that are constantly increasing. Okay, and the transformation rules that we've discussed, they still apply. So, for instance, if you put 4 in front of the tangent of theta, it's going to be a vertical stretch of the graph. So it's going to be vertically stretched by a factor of 4. Now, with sine and cosine, it directly, the vertical stretch directly impacts the amplitude. We don't really have an amplitude with the tangent function. Amplitude applies when we have a max and a min, and that's not happening here because these branches go up and down forever. So it's still a vertical stretch. It just doesn't affect any amplitude. That doesn't apply to this situation. Okay? Now if we move that 4, if we put it in front of theta, then instead of vertically stretching, we actually horizontally compress the graph, and the effect is the same that we saw with sine and cosine. If we horizontally compress, what we do is we create more cycles in 0 to 2 pi. So putting a 4 there would be creating 4 cycles from 0 to 2 pi. And let me just show you both of these. Okay? Put a 4 out here. I stretched those things out, right? Compared to that, that's stretched. And if I put a 4 here, you're going to see instead of those 3 pieces, you're going to see a whole mess of them, right? All of those in there. 4 cycles, so 4 times 3, there's 12 pieces happen in there. It's a lot, all right? So the same transformation rules apply. So now you can kind of hopefully recognize tangent when you see it. You're going to have asymptotes, and so periodically repeating asymptotes. The asymptotes happen every 180 degrees, because that's how often or how frequently cosine hits 0. And then we have branches that constantly increase in between. Okay, so there's tangent. Let's go on to the cotangent. So cotangent, if you recall, is just the reciprocal of tangent. So cotangent is the reciprocal of tangent. And tangent, we said, was y over x, which means on the unit circle this would be x over y. But remember, that's just cosine and sine, so we really want to be thinking of cotangent as the cosine of theta over the sine of theta. Okay, but we are using the unit circle, so if we want to just say x over y, totally fine. But those are all ways that we can be thinking about cotangent. So let's make a table and see what we can find here. Let's start at 0. If we're looking at 0 radians and we wanted our cotangent. So cotangent is cosine over sine. So 1 over 0 means this one's going to start undefined. And then we go to pi over 2. At pi over 2, we have cosine over sine, 0 over 1. That's going to be 0. At pi, we have cosine over sine, it's negative 1 over 0. Again, that's undefined. At 3 pi over 2, 3 pi over 2, cosine over sine, 0 over negative 1, that's going to be 0. And then when we go back to where we started, back to the full circle, we're going to be undefined again. So at 2 pi, we're undefined. So at 0, we're undefined. So we're going to start out with a vertical asymptote. At pi over 2, we're at 0. At pi, undefined. At 3 pi over 2, we're at 0. Oops, I drew that in the wrong spot. I can't see. It's so tiny. My poor eyes. Okay, at 3 pi over 2, we're at 0. And then again, full circle, 2 pi, undefined again. So not quite enough for us to make a complete picture. So just like with the last one, let's calculate a few more values. And you probably can guess what's going to happen, but let's not make any assumptions. So let's look at pi over 6. At pi over 6, if we take cosine and divide it by sine, radical 3 over 2 divided by a half, we end up with radical 3 over 1. So we end up with 1.7. So at pi over 6, we're going to be up here at 1.7-ish. And then at pi over 4, anything divided by itself is 1. So we're going to be at 1 here. And then at pi over 3, we're going to get 1/2 over radical 3 over 2, and that's going to be 0.6-ish again. So we do have these same values that we saw before, but this time we're decreasing. So we're coming this direction, we're decreasing, headed toward that point and getting closer to the asymptote here. And then as we turn the corner, we have this one again, 1/2 over radical 3 over 2. So that's going to be 0.6 again, but it's negative. So we're at a negative 0.6 again. And then here we're going to get a negative 1. And then here we're going to get a negative 1.7. And so we can see the same kind of behavior, but decreasing. So we're decreasing and approaching the asymptote this way. And when we jump over the asymptote, the same stuff's going to happen. At 7 pi over 6, negative is going to make a positive 1.7. And so we're going to see the same behavior, okay, where we're going to be let me go ahead and just plot this one in here. We're going to be decreasing. Oh man, I can't draw. We're going to be it's increasing this way. It's decreasing this way and approaching those asymptotes. Okay, so I did not draw that very well, but you can hopefully see what's happening. And I'll show you here. If we put in the cotangent of x, too many parentheses. There it is. Basically, it's a very similar graph where we have these asymptotes. This time, the asymptotes are occurring where sine is equal to 0, because this time it's the sign that's in the bottom of the fraction. So where sine is equal to 0 is where we have our asymptotes. And again, we have branches in between, but notice what's happening. In tangent, our branches were increasing. In cotangent, our branches are constantly decreasing. And that's how I distinguish between the two for myself, okay? Branches are constantly decreasing. And then the transformation rules, I feel like I missed a bullet. Maybe not. The transformation rules still apply. Now, we haven't really seen this transformation with the trig functions, but we know what happens when we add 2. When we add 2 after a function, it's going to make the graph, everything, it's going to shift up 2 units. And then we know what happens when we put a negative out in front. It makes the entire graph reflect over the x-axis. So let's just see. If I took my cotangent of x and then I added 2, then you can see that sort of inflection point has shifted up to 2. Okay? So everything just shifts up 2. Or if I take that away and I stick a negative here, then everything's upside down. Okay? Reflected over the x-axis. So the normal transformation rules, they still apply. All right? So now we've got tangent with asymptotes and branches that increase, and cotangent has asymptotes and branches that decrease. Next, we've got secant. Okay, so secant, been a little while since we've seen this one. Secant, if you remember, this is the reciprocal. Secant is the reciprocal of, which one do you remember? Secant is the reciprocal of cosine. Okay, it seems like cosecant should go with cosine, but it's like counterintuitive. So secant goes with cosine. A secant's reciprocal of cosine. So we said cosine was the x value here, so we're going to say it's 1 over the x value, but really we should be looking at this as 1 over the cosine of theta. Okay, so in the unit circle it's 1 over the x value, but really the x value is cosine, so we should be thinking of this as 1 over the cosine of theta. So again, we have this fraction happening, which means we have the possibility of having asymptotes. So let's make this table and see what's happening with this graph. So let's start at 0. At 0, if we take the reciprocal of cosine, the reciprocal of 1 over 1, that's 1. If we go to pi over 2 radians, the reciprocal of cosine, well, what's the reciprocal of 0? Well, that's going to be 1 over 0, which is undefined. And if we go to pi radians, go to the cosine, which is -1. The reciprocal of that is still -1. And then we're going to go to 3 pi over 2. 3 pi over 2. Reciprocal of 0 is not defined. And then full circle back to 2 pi, we get back to where we started at 1. Okay, so what's happening on this one is we have a point on our graph. At 0, we're up here at 1. At pi, we're at -1. And at 2 pi, we're at +1. That almost feels like our cosine curve. Remember how our cosine curve started at the max, ended at the max, and then hit 0 in the middle? Like, I could draw almost a cosine curve in there, right? But at pi over 2, we're undefined. Vertical asymptote there. And at 3 pi over 2, undefined. Vertical asymptote there. So what's happening in between? Let's figure it out. Let's look at pi over 6. Pi over 6, if I want the reciprocal of cosine, that's 2 over radical 3. Let's see, how much is 2 over rad 3? It's about 1.1. So we're going to be a little bit higher here. Let's just put it like right there. And let's go to pi over 4. If I take the reciprocal of that, 2 over radical 2. 2 over rad 2 is going to be about 1.4, so it's going to go up a little higher. And then if I take the reciprocal of a half, I get 2. So at pi over 3, I'm actually up to 2. And this is just going to continue to increase toward that asymptote. Okay, so there's one piece. And let's jump over the asymptote there. And let's look at getting the same values again, basically, right? So over here, this time the reciprocal is a negative 2. So at 2 pi over 3, we're at negative 2. And then at this guy, 2 over radical 2 negative, I forgot already. 2 over radical 2 is going to be negative 1.4. So negative 1.4 is like around here-ish. And then the reciprocal of 2 over radical 3, which is going to be negative. I should have just left it in here. 2 over rad 3, that was about 1.1. And again, that's going to be negative. So where am I at? Oh, I did put this in the wrong one. Sorry, 3 pi over 4, that's in the middle of these, was at 1.5. This is going to be 1.1-ish, and so it looks like we're approaching the asymptote this way. Okay, now what happens on the other side of that, this point, which looks really bad right now? What happens on the other side of this point? So let's plug in 7 pi over 6. 7 pi over 6, we get the reciprocal is 2 over radical 3 negative, and the 2 over radical 3, that was a 1.1. So now we're back to 1.1. And then this one's going to get us back to 1.4, so that's going to go down a little lower. And then this one's going to take us back to negative 2. So instead of having a branch that constantly increases or decreases, this one has a turning point. So we're increasing here, and then we turn and we're decreasing because we change signs when we change quadrants. And that means we have parabolas in between our asymptotes instead of branches. And what's going to happen on the other side here is the same thing we saw. This is going to be the start of a parabola that's going to be approaching this way. So our secant, and let's go ahead and just confirm, y equals the secant equals, well, 2 equals secant of x, and there it is. There's our parabolas. We're going to have parabolas this time instead of branches that are in between the asymptotes. So this one, we have asymptotes when cosine's equal to 0. Again, cosine being the bottom of the fraction. So when cosine's 0, we've got an asymptote. And this time there are parabolas in between the asymptotes. And the nice feature, something that helps me remember where the parabolas are supposed to go, is something I alluded to a little bit in the beginning here. My sine curve, my cosine curve matches up with the vertices of these parabolas perfectly. So cosine starts at 0, or starts at the max, ends at the max, and in the middle it hits the min. In between that is when it hits 0. If I was to draw or sketch my cosine curve into my secant graph, notice that the maxes and mins hit those vertices perfectly. So that is the cosine of theta that I drew in there. Okay, the vertices of the parabolas are the max and min points on my cosine curve. So that's kind of a nice little feature. So there's got to be parabolas, and what you want to see is those parabolas having vertices at the maxes and mins of your cosine curve. So if you can try to remember that, it's nice to know stuff, okay? Again, transformation rules still apply. So I put a 1/2 in front. That's going to vertically compress. So I'd be compressed by a factor of a half. And if I stuck a 1/2 in there, it's going to horizontally stretch the graph, or basically make 1/2 of a cycle from 0 to 2 pi. And I'll show you. Let me put a half here. You're going to see some compressed parabolas. I don't know if you can tell the difference, but they're compressed. And then if I stick a 1/2 here, we're only going to see half of that picture, half of that cycle from 0 to 2 pi. Okay? So there's secant. We got one more, and I bet based on this one, you know what's going to happen with this last one. So cosecant, if we remember, cosecant, this is the reciprocal of sine. Reciprocal of sine. So sine, we say, is the y value, then the reciprocal would be 1 over y. But technically, again, because the y value is the sine, we really want to be thinking about cosecant as 1 over the sine of theta. But again, we're on the unit circle, so if we just want to flip the y value, totally fine. So let's fill in our table. So at 0, if I flip the y value there, reciprocal of sine, reciprocal of 0 over 1 is 1 over 0. That's undefined. Okay, let me go to pi over 2, and then pi, and then 3 pi over 2, and then 2 pi. So at pi over 2, reciprocal of 1 is 1. At pi, reciprocal of 0 is undefined. At 3 pi over 2, reciprocal of -1 is -1. And at 2 pi, we're back to where we started, which means we're undefined again. Very similar. All these things are similar here. So this time at 0, we're undefined. That's going to be a vertical asymptote. At pi over 2, the graph hits not 0. The graph hits 1. At pi, we're undefined. At 3 pi over 2, -1. And at 2 pi, undefined. And you probably can guess what's going to happen just based on what happened with the last one. But just to be safe, let's go ahead and pick some points here. So pi over 6, okay, reciprocal of 2 over 1, or 1 over 2 is 2 over 1. So pi over 6, I'm at 2. And let me go ahead and jump to 5 pi over 6. 5 pi over 6, that's over here. The reciprocal of 1 over 2, 2 over 1. So I can see, again, I'm going to have a parabola in between my asymptotes here. And the same thing is going to happen on either side. So let me pick 7 pi over 6, just because they're really easy to flip. 7 pi over 6 is going to give me -2. And I'm going to go to 11 pi over 6, where again my reciprocal is going to be a -2. And so I have a parabola that's going to be in between these branches as well. And you know, you want to try to actually go through the points that you plot. It's helpful, but you get the picture. Okay, so there's our cosecant graph, and again, the vertices of those parabolas, they're specific. If I was to draw my sine curve, remember the sine curve starts at 0, ends at 0, and hits 0 in the middle, and then in between max, and in between here min. So if I was to draw my sine curve in here, draw my sine curve in the vertices of those parabolas, they hit that sine curve. So that's the sine of theta in there. Okay, so the cosecant function has asymptotes where the sine is equal to 0. Again, that's because the sine is the bottom of my fraction. I do not like that. That's the bottom of my fraction. And we have, again, parabolas in between, and the vertices of the parabolas happen to be the max and min values of the sine curve. And the transformation rules still apply. Again, not one that we have technically looked at, but is still true. If I was to subtract 5 from any function, it makes that entire graph shift down 5. So if I took, what are we looking at here? Oh, I didn't confirm this one. Let's go ahead and confirm. Y equals, forgot what we're doing, cosecant. My brain. And my eyes, that's what's happening. My eyes are failing me here. Cosecant of x, there's our parabolas in between 0 and pi, and then 0 and 2 pi. If I was to, after this, subtract 5, you're going to see everything shift down 5 units. Okay, so that's still a transformation that works. And if we did this, well, again, we haven't really talked about this, but it's still true. If I add or subtract after my function, it goes up and down. If I add or subtract with my function, with the theta or the x, it makes the graph go left and right. So that plus pi in there would make my entire graph shift to the left pi radians. And when we shift left or right on a trig function, I think I mentioned this before, we technically call that a phase shift of the graph. Now if I took this one and I shifted pi units, so think about this entire picture, if I moved it pi units, that's exactly that much, we really shouldn't see a difference in this graph. So let's look at this. If I just add pi in here, what's happened? Add pi. Oh yeah, we do see a difference. Wow, what am I thinking? Okay, if I take this one and I move it over pi, this parabola is going to land here, right? And then this one's going to land over in the next pi radians, and then the one that was over here is going to land over here. And I just put dots all over my paper. So this piece was, I can't point to it. This piece, it was over there before 0. It's shifted over, so everything's just shifted left and right. It's just that we call it a phase shift. And when we shift left and right on our trig functions, we want to shift by radians. So you'll usually see that phase shift, that translation left to right, by some radian measure in the parentheses. Okay, so hopefully you have a good idea, at least maybe you can recognize tangent, cotangent, secant, cosecant. You understand why there are asymptotes in those, and we see parabolas or branches in between, so that, you know, if you saw one of these functions, you can recognize it. So your assignment in Canvas isn't going to be like a crazy difficult assignment. I just need you to be able to recognize some of these things, okay? The focus is really on sine and cosine, so hopefully you've got a good grasp on those. So I think you have enough to get going on your practice, but as always, if you need some extra help, just reach out. All right, guys, till next time, take care.